El de la segunda presentación sí está ya conectado. Y bueno, el tercer ponente es en presencial. Pues para seguir con el horario, pero un poco más de tiempo. Second session on automatic control that has the title AC2. So first we have the presentation for the article that is entitled Low-Cost AI Driving Autonomous Rescue Bot for Water-Based Life-Saving Missions. The speaker is Shamik Mondal. This is going to be online, so let's wait for the speaker to connect. And in advance, I tell you, we will respect the time that is scheduled, so I will give the speaker at least few minutes less, and I will let him know about the time. Is he already connected? Yeah. Can you put it here? Yeah. Hi, Shamik. Please, can you put your presentation? And you can start. You're going to start with the presentation. Please turn off your camera at the same time. Okay, you can start, please.
The name of my paper is Low-Cost AI Autonomous Rescue for Water-Based Life-Saving Missions. So, first of all, I want to start with the objective part. So, basically, the main objective of my project is to save the drowning people from a situation where it's affected with flood. So, in flood scenarios, we see that the human gets drowned, and some people went there to rescue their lives. So our bot is to replace the human, and an autonomous rescue bot will arrive in front of the drowning patient and recognize his face and rescue him. And another objective of this proposed system is the system is a low-cost system, and it was built of some available market products, and the whole body was generated by myself. It's not being created with any made body parts. So this is my vehicle. It was created with a water pipe PVC board, and we have water make it waterproof by using some waterproof glues and some many other things. And we have also a camera here to recognize the human face, which is used to recognize the human who is drowning. And our whole system is trained with basically with some systems so that it can recognize the face. And There are also to power of this board, we have used battery, which is used to power up this board, and we have also used Raspberry Pi 4B. And there are some limitations in our rescue board. The limitations was it was running through a battery basically. I have shown it to you. So there is not emergency case system, which is implemented to charge the implemented when the battery charge is finished, and it can be but it can be solved using a solar panel on it. But we don't have any solar panel on it, as if it can perform its action with solar panel in case of battery has been get finished. And the system, our proposed system, is unable to rescue more than one person because it was a prototyping board. It's not made. It's not now basically made for industrial purpose. So after if we get industrial donation so that we can make it more stronger and more impactful. And this was the real time testing distance data. We have used RF beacon so that the RF beacon has been traveled from 0 to more than approximately 3,500 meters for his primary testing purpose. This was the path here, and basically
In this part of my presentation, we see that the human was risking the drowning patients who is being drowned here, and but we have tested in a swimming pool. Swimming pools.
so that you can see that it is able to rescue is able to detect the person who is being drowned and being rescued, and it can come back to the path which it had been came here, and it can detect some obstacles so that it can avoid the obstacles, and it can take the drowning patient safely into the place into the place which is dry basically. And this was the training matrix
that because I have told you that I have trained YOLO before, so it was a training matrix that I have found here, and you can see our training loss and validation loss here, and we have I can also I want to show you the confusion matrix because after testing it I have tested 12
images, and it can successfully detect almost 779 images, and sometimes it gets failed as if it was a proposed system, but it has been failed for some time, but most of the time it is performing its task nicely. And this was the human interaction model, how my system works. First of all, the human rescue board reached to the destination. You can see in the picture, and it can detect the human face by its camera and sends the capture image to the Raspberry Pi. So the Raspberry Pi processes the image in a model which is called YOLO V4 that I have trained for doing this project, and sends the measured distance to the Arduino Uno. And doing this Arduino Uno, it can generate the motor speed and the motor controller, and it sends the signal to the motor controller, and it reaches to the human, which has been detected by its camera. You have seen that I have implemented camera in my rescue board, and I have came into the conclusion. In conclusion, I want to say that we have successfully developed a fully autonomous rescue board, which is able to detect the human and navigates towards them in some flood condition. And you can see that it has been the system has been achieved more than 79% of reverse map accuracy, and it has performed low latency 115 ms, and it can perform the real-time operation. And the unique integration of this rescue board is we have implemented RF beacon, and we have also trained yellow V4 train it on Raspberry Pi so that it can detect the human faces, and we have tried to make it more cost effective and try to implement the GPS for this project. I want to integrate thermal cameras and an idea for improving its detection in low visibility conditions in night and murky weather when the weather condition is not basically because when in the flood situation you know that the condition of the sky is not so good. It was gloomy or almost cloudy. So my robo system is not too much able to do its performance in cloudy weather or low light condition. If I can integrate the thermal cameras on it so that it can do its performance better. And as if I have said that I have limitations, if my battery was drained and when it was unable to give the power supply, so I can implement some solar power system so that it can turbine the water turbine and I also want to implement water turbine generator for its long duration. So that's all. Thank you.
So we have time for several questions. Is there any question from the audience? No?
No.
I had a few points actually. Maybe you can see. Can you hear me well?
Yeah.
Yeah. Okay. If I understood well, your approach is more focused on how to identify the person that has to be rescued. That's right?
Yes, sir.
But in case that this is a problem with the water and it has to be rescued, maybe there could be waves or maybe also trash that is moving along the river or so on. So it can be an obstacle for the camera to identify the person that has to be rescued. So you mentioned now that you could integrate in the future work some other sensors like thermal and so on. But still, there could be the problem that the person is hindered by the obstacles, and then the camera cannot identify them. Do you have any other idea about that? How to solve it?
Can you? I'm a bit unclear with your voice. Can you repeat it again?
Do you have any other idea how to improve the identification of the person to be rescued?
Oh, I do. Do I have any other idea? Right. I have. Um. You can see that I have trained YOLO V4 model for performing my performing my rescue mission. But if I can train YOLO V8, the more better version of the YOLO model, so that I can tell that it can perform more better. And there is another limitations there that my camera is not so high-ended. So if I can implement a high-end camera here, so that it can able to detect the person more better. And you can see that I have get 79% of accuracy. So if I can do it, if I can train YOLO V8 model and can do increase the camera quality so that it can perform its performance more well. And you have tell me about the waves. It's the proposed system is able to perform its procedure in the in the wave situation. I have also tested in a river in my village. So it was bit slow there, but it can perform it well. It is not it's not it's not going in the wrong path. It can able to detect the human face as well, and it can do its performance better.
Okay. And another question. For the navigation purposes, you mentioned that you would use some beacons
Yeah.
to do the navigation.
Yes.
But then
Yes.
the idea is like these beacons has already to be installed in the area, or you will deploy them as soon as they are needed.
Can you repeat it more again, please?
Sorry?
Can you repeat your question again?
Okay. I mean, you are using beacons like to have the navigation area. But then the idea is like you will have these beacons installed before, or you will deploy them on the moment in the area that is needed.
Oh, well, that's a good question. I think you see when a flood situation occur in an area, there is a high possibility to become a no network coverage as if the area was flood affected. So when the area was flood affected, I want to trace my trace my system in a proper way. So when there is no network coverage, I will use the RF beacon.
I would make a suggestion or recommendation for you maybe to work with. Why don't consider a pair of robots? This water robot for rescue, yes, and a drone, such that the aerial vehicle can identify the person and maybe to deploy the beacons that are needed for navigation. And then this is going like to be a first task. And then the second task is for the water robot really to make the rescue. Maybe it could work out somehow.
You have told me to make a water vehicle, water robot, right?
Yeah.
Water robot, it was also a great idea, but I think the water robot is unable to float, I guess, because the water robot that you have told that it can be drawn because the water, I mean, you can see to my system that in my system that I have used some water pipes. So in the water pipe there is no particles inside of the water pipe, so it can be flown. But the robots, I guess it can be in the robots. I don't think that there is a propeller system there. But I have also a propeller. You can see here that I have used a Z thruster here. But I don't think that a Z thruster is being implemented in a robot. And the Z thruster was handmade because the ready-made Z thruster has been found in the marketplace, but we think that if we make them customized in our customized way, that it can do the performance more better.
Okay. Well, any other question from the audience? No. Okay. Thank you, Shami. We thank you for
so
your
much.
presentation.
Thank you. Thank you.
Thanks. A few minutes before the second scheduled talk. Ya está conectado, ¿verdad? Si lo pueden ir poniendo, por favor. Los dos últimos no están, ¿verdad? Todavía.
Ya.
¿Van a ser en línea?
Sí.
También.
Sí. Está.
Mohamed. Martín Reynoso. ¿Qué me decías que allá? Allá está la cámara.
Sorry, can you hear me? Please confirm.
Yes, we can hear you.
Okay.
I am the chair for the session, so I will introduce you first, and then you will have 15 minutes for your presentation. Okay. I will give you an announce of 3 minutes before the end of the 15 minutes. So,
yes.
Okay, we can start. So, okay, we will continue with the second talk that is scheduled. It has the title of Comparison between Kalman filter SLAM and particle filter SLAM applied to indoor environments in a mobile robot. The speaker is Jose Guarnizo. That's correct?
Yes, it's correct.
Okay.
Yes.
So you can start. And also, you put your camera, please? Yes.
Yes.
Thank you.
Okay, thank you very much for the presentation. My name is Jose Guillermo Guarnizo Marin. I am professor of Universidad Distrital Francisco Jose Caldas in Bogota. And this paper was a collaboration with Professor Cindy Paola Maya and electronic engineers Nicolás Álvarez Casadiego and Mario Armando Segura Albarracín, all together of Universidad Santo Tomás in Bogota. The problem and motivation of this research. Islam is a very important challenge in mobile robots in this time, in special in indoors where the lighting can change significantly, and SLAM performance depend on algorithm techniques and the kind of sensor employed. Two currently used approach for SLAM is Kalman filter and particle filter, each with different strength and limitation. In this work, we are going to offer an experimental comparison between Kalman filter SLAM and particle filter SLAM on a turtlebot burger with a kinetic sensor. For the programming, root operating system were implemented for the SLAM algorithm, and you can see in the image the presentation of our mobile platform robot. The objective is to evaluate how natural and artificial illumination can impact the localization and mapping accuracy. Our outcome is to provide a concrete evidence, in particular experimental evidence, for selecting SLAM algorithm based on environmental characteristics of the robot. And the research gap is a direct comparison of particle filter SLAM and Kalman filter SLAM under both natural and artificial lighting, because it's not enough addressed in the recent literature despite the foundational role of the SLAM algorithm today in mobile robots. We can check in the 3 last years previous work based on comparison of SLAM algorithms. We found different works. For example, here 3D LiDAR and visual SLAM. However, this work was focusing on sensor mounting position, the runtime, vibration, and effects of motion. Other work is a 2D SLAM comparison. However, the validation is in simulated environments. And its previous work was based a comparison of visual SLAM and LiDAR SLAM. However, it was focused on aeronautical flight scenarios. And LiDAR SLAM algorithms were compared in tunnel environment, only in tunnel environments. And other work presents a review of LiDAR SLAM algorithm for mobile robots, including experimental results. However, it does not involve visual SLAM. And in other work, we found the evaluation of 2 laser-based SLAM algorithms, GMapping and CARTO, in outdoor environments. However, we cannot find a direct comparison between particle filter SLAM and Kalman filter SLAM under both natural and artificial light, despite the foundational role. Let's quickly remember between particle filter SLAM and Kalman filter SLAM. In particle filter SLAM, the inference is not parametric, it's multi-hypothesis. The representation is weight particles per particle occupancy maps. Remember, one map, one particle. The update of the information is the sample, weight, resample, map update per particle. The trade-offs is handles multimodality in a higher computational cost. The computational cost of particle filter SLAM is higher, and the tuning is resampling needed. It requires more power of computation. In the case of Kalman filter SLAM, the difference is by extended Kalman filter using only a single Gaussian in the local linearization. The representation is by the mean and the covariance, Dubda's prediction, Kalman gain, and update in a one single map update. The trade-offs is efficient and the computational cost is lower, is low RAM usage. However, this algorithm is sensitive to nonlinearity and it could be some conflicts with data association. For the materials and methods, we use a Microsoft Kinect sensor. It has a red, green, blue camera for color image combined with a depth system that use an infrared projector plus a monochrome CMOS camera to capture the infrared projection. The Kinect captures depth-enhanced videos across a range of lighting conditions and other characteristics presented in the presentation. For the robotic platform, we will use a differential mobile robot Turtlebot 3 Burger. It is a small, affordable, and programmable two-wheel robot, very simple but robust. Usually is used robot operating system for the program of these platforms. It's compact, modular chassis support, a different kind of range of sensor and configuration. In general, it's a low-cost platforms. And the sensor data and the ROS integration, the red, green, blue, and the depth stream is published using the frenetic launch of the ROS package. These topics are compatible with SLAM nodes, and the red, green, blue depth integration provides both the visual and the geometric cues, improving the extraction feature and post-estimation under indoor lighting. We use the red, green, blue depth SLAM. It's a special solution for ROS designed for this kind of camera. The outputs are the current camera pose, and it can generate register point clouds or maybe Octomask. We use point clouds. It enables fast acquisition of two-dimensional or three-dimensional colored models of indoor scenes using a kinetic camera, for example, for our case. The core task is landmark recognition, motion estimation, map building, and lobe closure detection. It's an open source system in general, and we can use the plus color features for the description and data association. And color plus depth cues improve the mapping and localization robustness in indoor environments. For the experiments, these experiments were performed in the robotic laboratory of the Universidad Santo Tomás in Bogotá, Colombia. The experiments were conducted indoor lighting conditions inside the robotic laboratory. We worked two different kinds of experiments, natural daylights with the open windows of the laboratory during the day, and artificial light with the closed windows at nights. The road follow a predefined trajectory for the mapping process. Setup enables measuring localization and path tracking accuracy and comparing routes with a ground truth. Computed localization and tracking error were used in order to evaluate the algorithm performance. The algorithm evaluate was SLAM based on the Kalman filter and SLAM based on particle filter. Control node trajectory tracking controller. The road runs were manually teleoperated using Turtlebot 3 teleoperation key associated with ROS. And input to SLAM the well odometry of the robot combined with the visual SLAM. The experiments, 4 experiments were performed, follow this trajectory. We starting here in the corner AC and follows the trajectory, the external trajectory. You can check the external trajectory starting in the corner AC and finish the trajectory in the corner AC. 2 runs algorithms for SLAM were performed, particle filter, G mapping, and extended Kalman filter. The lighting condition, as I described, in the day with the windows open and in the night with lighting, standard lighting, controlled lighting, with the windows closed. The observed values was on site the measured distance in meter of the trajectory. And the predicted value was odometry based estimation in meters at the same waypoint. We obtained the difference prediction observed in the signal error using to computer root mean square error, follow the trajectory described. This is an example of the maps obtained using the RBS applications. For the G-mapping algorithm, natural light and artificial light, we can see an approximation of the trajectory. And we report the result in 4 tables. And we can check the observed value, the predicted value, the difference, and the root mean square error of all the 4 experiments. G-mapping algorithm in natural light, in artificial light, and extended Kalman filter algorithm in natural lights and in artificial lights, taking the root mean square error for the comparison. In general, G-mapping particle filter SLAM obtain always a better performance than extended Kalman filter SLAM, obtaining always a root mean square error less than extended Kalman filter. The best case, yes, the best case was G-mapping under artificial lights, obtain a root mean square error less than G-mapping natural light. Similar case was with extended Kalman filter SLAM. Artificial light obtain a less root mean square error than natural light. However, G-mapping obtain in both cases, natural and artificial lights, a root mean square error less. Particle filter based SLAM shows a consistent advantage, especially under artificial lighting in indoor environments. The conclusion: implemented and experimentally compared extended Kalman filter SLAM and G-mapping particle filter SLAM on a differential drive robot using a Kinect under natural and artificial indoor lighting, using rows like pipeline in a predefined loop. Root mean square error was computed for odometry against in situ distance reference. G-mapping consistently achieved lower error than extended Kalman filter SLAM, with best performance under artificial light conditions. Both algorithms perform better with artificial illumination, indicating more stable observation and lower post-error estimation. And we can check or confirm that using Kinect point cloud, we can obtain a 2-dimensional laser scan for an effective identification, the SLAM identification, maybe creation. However, we are not working. Our paper is not focusing on the mapping, it's focusing on the localization. In general, my consideration, the most important conclusion for our work is if you need to reference that a particular filter for visual lab obtain a better result than Kalman filter, you can read our paper and to reference our paper if you consider this result is adequate for your research. For future works is to replicate the comparison using a 360 degrees LiDAR and alternative with visual sensor, for example, RealSense. Stress tests with 2-dimensional SLAM up to lighting change or extend to 3D capable formats. And this is an example of how can obtain a 3-dimensional map of the robotic laboratory with these algorithms, and to port this model ROS distribution and include pipelines that maps 2-dimensional data to 3-dimensional representation, as we show in this. This is the reference. And do you have any questions?
Thank you very much. So we thank the speaker. And we have time for several questions. Is there any question from the audience? Actually, I have.
Yes.
Now, the conclusion seems very, understandable. That this particle approach is better in some conditions with respect to extended Kalman. But as you mentioned, one drawback is the computation load that it requires. So if I understand well, you take the images and then you send to a computation node or a computer outside the robot, and then it gives the information from the SLAM. Is that correct? Because you are not doing the computation on board.
No, no, no. It's by road. I sure you know, Ross, you can, this particular robots, the TurtleBot, work with slave, master and slave. The computation is in the master, and the slave is only for local control of the robot and streaming of the information.
Yeah. Because also the other question is, you mentioned as future work, like maybe to compare also with LiDAR, because these robots are usually supplied with the LiDAR and also depth sensor. So maybe you consider the integration of all the possible information. Obviously, it's going to be a much larger data to be processed, but at the end, it will improve the SLAM with all the integration information.
Yes, I consider a very interesting next step into research is using three-dimensional LiDAR. I consider it could be too interesting not using the visual SLAM, because the three-dimensional LiDAR has a lower computational cost than the image processing. We consider for future work the use of the three-dimensional LiDAR. This representation, this TurtleBot, it has a LiDAR, however, is only two-dimensional LiDAR, and in fact is very limited, but I consider too interesting this comparison with the three-dimensional LiDAR.
Great. Is there any question from the audience? No, not anymore. Okay. Well, thank you very much for the interesting presentation. We thank you once more.
Thank you very much.
Awesome. Okay. Next speaker is here. I know he's going to be in person, so that's nice. Okay. But we had people that disconnected. That's right. Online. Okay, great. Tenemos 2 minutos. We have 2 minutes. Bien time. Okay, the third article of this session has the title Safest Sliding Mode Control in Position for Double Integrator System. The speaker for this article is Marco Gomez. So please, you can start.
Yes, I'm going to present the results reported in the paper entitled Safe Sliding Mode Control in Position for Double Integrator Systems, which were obtained in collaboration with Christopher Diego Cruz Ancona from Tecnológico de Monterrey, Campus Querétaro. Sorry. Okay, so the outline of the presentation is this one. First, I'm going to present the problem that we are approaching. Then I present the main results, and I conclude with some remarks. Next one, please. Yeah, the class of systems that we are considering is this one, double integrator systems, where G corresponds to the input matrix, which is assumed locally Lipschitz and non-singular. U is the control input, and X and dot X are the states of the system. And here we are considering uncertainties and disturbances characterized by delta. We are assuming that the norm of this delta is bounded by a function d, which is known. Now, in the paper, we are also considering some disturbances or uncertainties in the input matrix, but we don't need it here for the presentation of the main ideas. So the objective of the work can be stated as follows. We want to construct a sliding mode control strategy to guarantee that the closed loop system trajectory remains within a given set in the position coordinates of the state space. I think that we can understand the problem better if we consider just the double integrator with position and velocity scalar. We give a set, in this case, set C, given by this expression from here. And what we are looking for is that if we start at any point of the set C, we want that the closed loop trajectories remain within that safe set C, right? So I will refer to this set C as a safe set and the complement of this set as an unsafe set, right? So from the sliding mode control point of view, we can achieve the objective if we propose a sliding surface or sliding manifold in this way. And it should be clear because with a standard sliding mode control, we can ensure that if we start near the sliding manifold or the sliding surface, or if we start on the sliding surface, then we will be within there for all future time by converging to the origin, right? So for this case, when we have position and velocity, scalar position and velocity, the problem is already solved. But what happens when we increase the dimension of the double integrator? Let's consider, for example, a position in R2. What's the problem with this? That the safe set might have some more complex geometries. For example, if we consider as an unsafe set this circle from here, the safe set will be the complement of it. And if we consider just for example, this sliding manifold, then we will have the vectoral field that is shown in this figure allows to see that indeed for some initial points, sooner or later we will cross the prohibited set or the unsafe set. So now the question is how to construct a suitable sliding surface that allows to construct a robust sliding mode control that guarantees safety or that the position coordinates, the position remains within the safe set C. To be more formal, I'm going to define this set C in this way, where the constraints in position are encoded by the set C1, and we don't impose any restriction on the velocities, right? So the main proposal of the paper is actually this one. We are proposing this sliding manifold, where the sliding variable is given by this expression. So that x dot, of course, is the velocity, and b of x is the function that we want to design to achieve our objective. So now the question on how to construct a suitable sliding surface translates to the question on how to construct b of x. We are looking for a b of x such that the dynamics of the simple integrator, this one, remains safe. So we are focused on the reduced dynamics because indeed, when the trajectories are on the sliding surface, we can say that x dot is equal to b of x, right? And it turns out that this b of x can be designed by using the notion of control barrier functions. And it can be constructed by as a solution of optimization problem. The solution in this case is given by this expression from here, where B des is a desired velocity, H is just encoding the constraints in the position. And for example, if we consider just the simple integrator, we can construct this B of x such that indeed the simple integrator dynamics guarantees safety of the position trajectories, just as it's shown in this vectorial field. We can see that we can avoid the unsafe set in red from any initial condition, right? And it turns out too that indeed this B of x can be constructed in an explicit form from this expression from here. This function is not smooth, but is locally Lipschitz. So anything is fine with this. So with this sigma, we have the standard unit control, sliding mode control in this form, where we can see here, okay, rho should be, rho is given by this expression from here. It depends, of course, on the function that is bounding the uncertain terms. Kappa is just a gain greater than 0. And that's it. We can say the following. If the assumptions on the uncertainties and disturbances are satisfied, then the set S is a safe sliding domain for 1 in closed loop with 2, my controller 2. I'm avoiding some definitions, but what the theorem is telling us is that if we start near the sliding surface, then we can guarantee that the trajectories will remain within the safe set C in position, right? But this is not all, because here I'm talking just about the sliding phase. I'm not talking about the reaching phase. That is what happens when we are far from the sliding phase. We can prove that if we choose the gain kappa in this form, indeed, before the trajectory hits the sliding surface, the trajectory will remain within the set SC. So we have this corollary from the above results that says that system 1 in closed loop with 2 and gain 3. This is gain 3. Then the closed loop trajectories will remain within the set C whenever we start within this set C, right? And that's the main result. Just a brief example. I'm considering, and okay, I think that we can see it better in the figure. I'm considering this obstacle here. This is the unsafe region. And of course, the safe set corresponds to the complement of it. I'm just showing the position coordinates. I'm considering a double integrator in R2. So yeah, the result of the controller is in the coordinates, in the position coordinates is shown in this figure from here, figure A. In figure B, we can see the evolution of the states, of all the states with respect to time. In figure C, we can see the control signal. And in figure D, we can see the evolution of the sliding variable along time. Now, we can see that here we have an overshoot in the control. It has to do with actually with this term from here. But I'm not presenting it in the slides, but in the paper, there is a smooth parameter that helps us to reduce that overshoot. Okay, conclusions. For double integrator systems, the design of a safe sliding domain in position coordinates was proposed, which allows us to propose a robust controller for guaranteeing that the position state will remain within a given set safe C, given safe set C. And the proposed approach may be particularly relevant, for instance, for robust obstacle avoidance in robotics when the model of the robot is not fully known. And of course, we can also extend the idea for for systems, for more general systems, higher order systems. Okay. And that's really
Well, we thank the speaker. And we got time for several questions. Any question? I have.
okay. Yeah.
Yeah. Well, I was first a bit confused about the idea why to use that adjective of the term safe instead of constraint, because at the end you are converting the problem into an optimization problem, and in optimization this function C actually is a constraint to find the solution of optimization problem. So
Yes.
why to decide for the safe?
Actually, the constraint, you can see that the constraint doesn't come by h, explicitly by h, but by the gradient of h.
Yeah.
So I don't know if it is what you mean, but when we talk about the quadratic program, the constraint in this case is not the same as the constraint in the state space. I mean, it's related, but yeah, from a terminology point of view, it's not the same.
Yeah, what happened? I was wondering about the terminology because first I was thinking like safe, maybe it's like when a robot has to avoid some obstacles, some
Yeah,
possible
it's-
collision and so on.
Yeah, indeed.
So you decide a safe path or safe waypoint,
Yeah,
but in here it's actually the constraint that you are getting.
yeah. The terminology comes from actually from the notion of control barrier function, but what we are talking about is indeed control invariance, the concept of control invariance.
Yeah.
Yeah.
And the other part was that actually, I see that you depend a lot of on the gradient of the constraint by itself. But then you need, I think, some constraints and some requirements about that constraint. For instance, has to be continuous.
Yes.
It's the common that maybe you have not leaches is not enough, or maybe some uniformity along the set that has to be defined. I mean, that is not growing with the escape, anytime escape. Otherwise, the gradient can be undefined.
No. Actually, the function h has to be continuously differentiable, and the gradient of h has to be also locally Lipschitz. It's enough to be locally Lipschitz.
Yes.
Yeah, the gradient of h. Yeah.
Yeah. Otherwise, it's
Yeah. This is based on this a formal definition of control barrier functions where. Well, I'm omitting all these definitions, but in the paper is explained. Yes.
Okay. And now that you mentioned, because I was wondering also which kind of systems you have the general dynamics of the system, but thinking also on the safe program and systems that can be modeled by two states. I don't know, maybe a robot or whatever or something. As you think about a possible application or more general result for simulation, like to test the approach?
Yeah, indeed, there is a master student in the department that is working with a mobile vehicle, and he's trying to apply this strategy to that case. But because at the end, at least with the class of vehicle that is that he's working with, it can be reduced. The model can be reduced to a double integrator system. Yeah, and in this case, the constraints correspond to the obstacles. Yeah.
And just the last one.
Yeah.
For me, it was interesting to see how you define the sliding mode.
Yeah.
I think it's more common like to have X product X dot
Product
negative.
dot. Yeah.
So for me, it was interesting to see that now you define this sliding surface sliding equation in that way. So
yeah, but indeed, V of X is composed by two components. You can see. Okay, I don't know if this is what you mean, but you can see here. V of X at the end depends on these two components, and for example, V des corresponds just to X. Can be correspond just to X, and the new term is this one from here. And from this expression, you see that there will be some times where where this is 0, and other times where this is different from 0. When you are far from the obstacle, you just recover the standard sliding variable.
now you go back to the previous another one. That the idea is like to define Bx, you define this sigma x like this equality to 0. But usually in sliding modes, it's like you have X position times x dot
Ah.
less than equals 0.
Yeah.
So it's like somehow you relax more the sliding of constraint. In this case, it's like you are forcing equality to 0.
No, I'm not sure. It should be equivalent, actually.
I think
It should be equivalent. And with this expression that you are showing, what it's saying is just in which side of the yeah.
it's
here.
completely equivalent.
Yeah, it's completely equivalent.
In
Yeah,
that sense.
indeed.
Yeah.
Yeah.
I was surprised.
Yeah, I don't know how this expression would be modified with our proposal, but for example, when you consider this one, it should be equivalent. Yeah.
Yeah, but I think that's even a stronger constraint with respect to this one because you have that quality to 0. And in this case,
okay.
it's less than, so it's like the solution may be a bit
Okay.
larger space, maybe, but
Yeah.
it's
Well, we can
just-
talk later, but yeah.
Okay.
Or if we have 2 minutes, I can try to clarify it.
No,
It's okay.
I think there are some equivalents, but maybe in the case of the equality.
Okay.
Okay. Is there any question? Audience? No. Thank you very much. Again. We have a few minutes before next presentation. Okay. It's already connected, that's right?
Yes.
Hi, Victor. Good afternoon. Can you hear
Hi,
me?
everyone. Well, good afternoon.
Good afternoon. Can you put your presentation, please? To
Yes.
introduce you. I will introduce you, then you will have 15 minutes for presentation. I will let you know when you have 3 minutes remaining of your presentation.
Okay, thank you. Do you hear me?
Yes.
Can you
Yeah, we can hear
see
you
the
well.
presentation?
Yes. Already.
Okay, thank you.
Can you put it full screen?
Yes.
Perfect.
Yeah. Can I minimal? Okay. Okay.
Perfect. So we are on time. So, okay, the next presentation for this session on automatic control has the title STA-based design of a fixed time convergence disturbance observer for autonomous underwater vehicle. The speaker is Victor Marquez. He's already connected, so please, you can start.
Thank you so much. First of all, good afternoon, everyone. I'd like to thank you for being here and for your interest in this presentation. I hope you find it useful and informative. My name is Victor Marquez. Okay, I am a master's student in Center of Engineering and Industrial Development in Querétaro, Mexico. This presentation is based on my research project titled STA, based design of a fixed-time convergence disturbance observer for autonomous underwater vehicles. My advisors are Dr. Jesus Guerrero, Dr. Tomás Salgado Jiménez, and Dr. Garcia Valdominos. And this is how the presentation will be structured. Our main focus will be the methodology and, of course, the results. As an introduction, I'd like to highlight some important aspects of the underwater vehicles, such as their typical and main applications. They can be classified according to their level of autonomy. On one hand, we have the autonomous underwater vehicles, which can perform tasks without any human intervention. On the other hand, we have the remotely operated vehicles, which are controlled by an operator. In this work, we focus on a robot that combines the both characteristics. And in the recent years, underwater vehicles have become an essential tool for maritime missions, such as environmental monitoring, sample or treasure recovery, and oceanographic exploration. Underwater vehicles face several challenges during their operation. Among the most common are disturbances, which may come from external sources, such as ocean currents, changes in water density, or environmental variations. Another challenge is the difficulty in accurately modeling the system, which leads to the parametric uncertainties. And from the control perspective, nominal controllers often lack robustness, making them less effective under these conditions. To address these issues, the literature shows that the most research effort focus on developing robust control methodologies, combined with the application and innovation of advanced control strategies. In recent years, several control strategies have been proposed, like sliding mode control, backstepping, high order sliding mode control, artificial intelligence techniques, and adaptive control methodologies. But is there another way instead for applying complex control methodologies? Yes, and that's where the disturbance observers becomes an effective solution. Okay. In this slide, we can see the mathematical model of underwater vehicles, which has been extensively studied by authors such as Fawcett. This model includes several key components: the inertia matrix, the Coriolis and centripetal forces matrix, the hydrodynamic damping effect matrix, and the gravity and buoyancy vectors. Ideally, these terms are balanced by the control input and the disturbances acting on the system. From the figure, I would like to highlight the references frames, the body fixed frames, and the earth fixed frame. In particular, notice how the body fixed frames illustrates the rotational motions of the vehicles around its axis. To simplify the formulation, we can use the transformation matrix expressed earlier in the equation 2 to obtain a single reference frames, which leads to the expression shown in equation 3. It is difficult to accurately estimate parameters that remain valid under all operating conditions of the vehicle. It is more practical to work with an estimated model represented in equation 4. Finally, the disturbance vector gathers all variables that may affect the system's behavior, including the unknown dynamics, like seen in this slide. In this work, for comparison reasons, we use two nominal controllers, like PD, the proportional derivative, and the PID, proportional integral derivative. Both are based on the error dynamics, which simply means the difference between the desired and the actual position or trajectory. As an important part of this work, we introduced the super twisting algorithm. It is designed to improve robustness while reducing the shattering effect, typically present on the classical sliding mode control. As shown in this slide, the controller consists of two ports, the The first one, considered by the variable tau, depends on the sliding variable sigma and its sign. And the second term, phi, introduces an auxiliary dynamic that helps smooth and control action. In simple terms, this algorithm forces the system to reach and stay on the sliding surface infinite time, ensuring robustness against disturbances and model uncertainties. The design of the observer is based on the structure, actually in the super twisting algorithm, as shown in equation 9. This observer allows us to estimate and compensate external disturbances affecting on the system without requiring prior knowledge of the origin or exact model. The main idea is that from the difference between the actual output and the estimated one, the observer generates a signal to converges to the real disturbance value. In this way, the system can correct its behavior, maintaining stability and improving control performance. The time-based generator is defined using a fifth-order polynomial. Its purpose is to allow to the user to specify the duration of the smooth transition through a parameter called TV. The polynomial is used to create a time-varying gain, helping to avoid abrupt changes in the observer's response. The TVG is defined in equation 10 and its time derivative in equation 11. The time-varying gain mentioned earlier in the slide before is defined as shown in equation 12. Its gain allows the observer's intensity to be adjusted over time, ensuring a smooth and controller transition during convergence phase. Theoretically, the disturbance estimated by the observer becomes equal to the actual disturbance acting on the system at time TV, mentioned in the before slide. In this way, the controller, which is in this case is a PD controller with the observer, is defined as shown in equation 14. The purpose of this formulation is that once the estimate disturbance is substituted into the model, the real disturbance are compensated or cancelled, resulting in a direct relationship between the dynamic model and the controller. To evaluate and compare the different control strategies, we use the root mean square error. This is a common metric used to measure system accuracy, and it is defined as shown in equation 15. Now, let's take a look at the results obtained for each control strategy under different test scenarios proposed. Sorry. For all cases, the desired depth trajectory was programmed to generate a smooth polynomial signal in 2 stages. In the first stage, the vehicle moves from an initial position representing the water surface to an intermediate position of 1 meter over a defined time interval. Then it maintains this position constant for a fixed period, and finally performs a second transition toward a final position of 0.6 meters. In the nominal case, an ideal scenario is considered, ignoring any disturbances. In the parametric uncertainty case, an additional object is simulated, modifying the vehicle's aerodynamics parameters, similar to the effect to the additional object on the structure in the underwater vehicle. And the external disturbance case, time-specific perturbations were applied to the robot while it follows the reference trajectory. They represent non-constant ocean currents or sudden impacts of the vehicle structure, which can affect the stability in the performance. The goal of these disturbance scenarios is to evaluate the controller and performance in reacting to both gradual and sudden changes, ensuring stable tracking and fast recovery from external effects or disturbances. For the nominal case, the results were okay. Before showing the results, it's primordial briefly explain the plot configuration. The black dashed line represents the desired trajectory. The blue solid line corresponds to the PD controller, the yellow one to the PID, and the green one, the STA. And finally, the red line represents the PD controller with the disturbance observer. In the plots, the y-axis represents the depth in meters, and the x-axis represents the time in seconds. In the nominal case, where no disturbances are applied, all controllers achieve good tracking of the reference. Maybe the PID with the blue line seems to show a not noticeable error during the transition stages. And this error is actually quite small, as will be confirmed later in the quantitative results. For the observer results in this plot, we can see these real disturbances shown with the black dashed line, similar like the past scenario, and the estimated ones in the red line. After the predefined time, the observer becomes fully active, accurately capturing the magnitude and the timing of each disturbance. It's important to note that the observer does not identify the origin of the disturbance. Its implied considers any factor that affects the system stability as a disturbance. That's why during the transition period, it produces small estimators, if you can see in the plot. While once the system becomes fully stable, the observer correctly estimates no activities disturbances. In this case, the effect of the disturbance on the system becomes more noticeable in these parametric uncertainties, especially when using the nominal PD controller. However, the PID, STA, and our technique still manage to follow the reference trajectory without significant difficulty. Now, leaving aside the transition periods mentioned earlier, the observer successfully estimate the disturbance, providing an active and efficient compensation. This confirms that the observer can accurately detect and counteract parameter variations. In this final case, the external disturbances, the advantage of the proposed technique becomes more evident, since the nominal PD and PID controllers are strongly affected by the external disturbances. In contrast, the STA and our technique maintaining a more stable tracking with a smaller deviation from the desired trajectory. And from the observer results, the observer accurately captures the magnitude and timing of each disturbance, even under abrupt changes, like in this slide. This demonstrates its high responsiveness and robust estimation. In terms of
We have one
quantitative
more minute,
results,
please.
in terms of quantitative results, the root mean error shows that the proposed technique significantly improves the PD controller's performance. The difference between the STA and our technique are minimal. To conclude, I will take a moment to read the text shown on this slide.
Okay.
In this work, I fixed a fixed time STA-based disturbance observer was proposed, introducing a time-varying gain that allows the user to specify the convergence time. Simulation results show consistent performance improvements compared to the nominal PD and PID controllers, reaching a level close to advanced control strategies like the nominal STA. As a future work, real-time experimental validation under fast and time-varying disturbances is planned. And there are all references. That's all for my side.
Okay, thank you very much. So we have time for some questions. No. Okay, I do. So far I saw the proposed controller you use is taking into account parametric uncertainty on the model. Yeah.
Yes.
And it's well known that these super twisting and high order slide mobs, they are quite robust against these sort of uncertainties. uncertainties. What I am a bit worried is that the equation for the controller and for the definition of the sliding surface, you are using the velocity of the system. And then it's always noise on that signal. And mainly on underwater vehicles, actually the velocity angles or the rotational velocity of the body of the vehicle are quite noisy and quite hard to get. So how robust is actually you propose, but against this kind of problem with velocity dependency?
Okay, we really think that using the STA algorithm, we can counteract this kind of the problematic. For example, sorry, I think the main approach of this technique is that we don't use any estimated model. The natural. Sorry, I can pay the. Okay, sorry. Okay. In this slide, I present that the observer in a time TV, the estimated disturbances are equal to the disturbances acting on the system, and we are considered all the variables unknown dynamics and all the variables that we don't know, like disturbances. So the observer, in our perspective, can counteract these variables unknown.
Yeah, but I mean, for instance, in that equation 14, KT is multiplying the velocity error. So that depends on the desired velocity compared with the measured velocity. And then that's my point, that it depends on the velocity. And sometimes you had the dirty derivative for the position to get that velocity and so on. So that's what I mean, robustness against velocity measurements, noise and certainty, but that's okay. Maybe you can try out some simulations like to check out. There are some techniques actually, maybe not with finite time convergence. Like maybe you had heard about this ADRC, active disturbance projection control, that at the same time estimates disturbances or perturbations, but also the velocity.
Okay.
Maybe you can consider some ideas, but
Yes.
Thank you very much for your
Thank
presentation.
you so much.
Success. Well, thank you. So we have time for next presentation. We have a couple of minutes.
Thank you.
Next one is going to be online. Thank you. Have a nice afternoon. Mohammed is already connected.
Yeah.
Hello.
Hi, Mohammed. Good
I
time,
can't.
I think.
Yeah, I think I can present now. Thank you. Can you see this?
Wait a minute. We are just going to. Yes, now we can see your presentation.
You see?
We have 1 more minute before starting. Just wondering what hour is in your place, Bangladesh? I think it's really quite early in the morning.
Yeah, it's like 5 a.m. I've been up all night preparing for this. It's pretty late. What time is it there?
Actually, yes, we are now about beginning. Here is afternoon.
Okay.
It's 10 to 5. Yeah. Okay, so the next presentation has the title Offline Vehicle Tracking System using GPS, GSM, and Android. The speaker is Mohammad Rehwan. I don't know how to pronounce it properly. Thank you. And well, you have 15 minutes for your presentation. I will give you an announcement, a notification, that you have 3 minutes remaining. So you can start.
Thank you for the introduction. My name is Mohammad Bayat. A little correction on that. So I hope all of you are having an amazing day. And today I will be presenting on behalf of my team, and I'll be discussing about our project on offline vehicle tracking system using GPS and GSM module and Android.
Okay.
So, when we were talking about offline and online, like when we were discussing what to do a project on, one thing we all wanted to do is we wanted to talk about what really mattered in our country. So, one of the biggest issues in Bangladesh is traffic, right? And apart from that, you would be surprised to know that like 60% of people don't use emergency vehicles like ambulances to go to hospitals, and that was one of the key issues that was discussed in a paper written in 2017. So in that paper, when the survey that came out, it told us that only 11% of people actually use ambulances. So we wanted to know why was that, like what's causing that issue, and we wanted to fix on that. We wanted to move towards that, right? And not only was the traffic an issue, it was other things as well. One was location tracking and dispatching. There are no services that actually have ambulances or emergency vehicles and things of that sort. Second was internet-based issues. So there are a lot of places in remote areas in Bangladesh where the internet services are really bad, and that causes a very big issue, even if there is an app or even if there is something like that. So we decided that we are going to make something that is offline, that brings everything together and basically gives us a solution which can be used in every aspect of Bangladesh in this aspect. So let's first focus on what were other solutions that people came up with and why is our one better. So there were different research on GPS and GSM modules, but most of them were required internet either, or they were just not good, they were very not cost effective. Our one brings all of them together and gives us a solution which is not just cost effective, it works without internet, and we are offering everything in together using an app also, and it uses internet as well if you want to use it, but if there is no internet, it still works perfectly fine. So before I tell you about what my project, let's see what components am I using, what things did we use. First of all, before I tell you about my components, we had a lot of issues. We actually burned through 3 different GPS antennas before actually making the system, and it was mainly the problem was thanks to our guy who was working with the hardware and stuff, that he found out that we should actually use a buck converter to lower the voltage because the voltages for Arduino and the GPS were different. And first of all, we were using an Arduino Uno R3. We were using a SIM GPS GSM module, which was paired up with an GPS antenna, which basically connects to the satellite and gives us coordinates. And we're also using a battery just in case, because when we connect this to a vehicle or any place here, so we're just having this as a device even, we obviously won't have power like from a laptop, right? So we would have to use a battery for that. And that's the reason why that is there. And also because the buck converter is there. So how does it work? First of all, so we're using a serial library that symbolizes like the SIM module. So when we turn on the GPS module, it basically connects to the satellite. It gets the coordinates. That coordinates are sent using the SIM module to a phone number. Here's the trick. We have an actual app that we made using Android Studio and Java that basically fetches that coordinates and puts it in the app so that we can see where that vehicle is exactly at. So this is an actual simulation of the message. If you see here, this is the message, this is the coordinates of that particular place, and we can actually see that place. So, and this uses Google Maps API to do the entire thing. So we already have that algorithms and everything inside of it, and we don't have to do anything apart from that. So for example, if someone's using our app and he says, how do I know that the vehicle is coming as fast as it can? So basically it's using Google, so which has a very good algorithm already. We don't need to implement that. That solution is already there. We're just taking it there and we're just using it, right? So apart from that, why is our like thing so good in terms? One thing, it's very small, it's very compact. We just use different wires to connect everything together. And one of the reasons is so that it's just robust. It's just easy to use and it's easy to fix anywhere. For example, if you're in a hiking, if you're somewhere in a hike, okay, and you just got lost, you don't know where you're at, you can just use that device, tell your friends that just send them your location and they'll just track you. They'll just be there, right? And this is one of the key things we were working on. Apart from emergency responses, this was one of the things we always wanted to do. And this is one of the UIs we built after the initial implementation. This was a simulation. So we actually had like hospitals nearby, and we were like pairing up with them and actually do it. So actually have a simulation running so that we can see is our service running or not. Okay. So when we were developing the hardware, like I said, there were a lot of issues. So this initially we were just powering with the computer and we were trying to see how it works. And this was working perfectly fine. But the thing was, the solution shouldn't just be on a computer. It should be along with the battery so that it is remote. It is something we can take to parts, right? Because it will be connected to a device, or you would have it in your hand. And yeah, so this was one of the reasons why we went with the lithium battery in the end. And this is our packaging done together. Although it looks like a mess, I can assure you this works perfectly fine. So when we were done with the packaging, we were done with everything. This was time for like results. So what we did was we booked up an Uber. We went to a 10 kilometer like a road, and we were like, okay, we're just not gonna have straight roads. We're gonna go for turns and different places, high altitudes, low altitudes, and even water bodies, so that we can see where exactly things align, where exactly do like our readings look good and where they don't look good. So apart from this, we also did results like experiments indoors, outdoors, near water bodies, and on a moving vehicle. So as far as I can see, when we were doing the test for a moving vehicle, results were pretty good, considering it's just a small GPS antenna and it's just connected to the satellite. Most of our outdoor like GPS accuracies were 8 to 10 meters during road level, and when it was near water, it averaged almost 7 meters plus minus. And indoors, it was slightly weak because come on, like we're under like buildings and stuff, so signals are eventually get weak. So that was 20 meters, and the GSM response module was 5.6 outdoors, and when we were just moving, it was 5.9. So yeah, and so after that, we were like, okay, let's discuss what happened. Why is everything okay or not? What we came up with, we actually tried this solution and see like get user feedback, because this is something we actually want to implement in our country because it's a big issue. If you think about it, me personally, when I go out on the road every day, I see different ambulances and people just going on literally buses and like motorcycles to hospitals. So this is a solution we already wanted to come with, and that's one of the reasons why we went to people and be like, would you allow yourself to use this? And they were happily into it, and solutions actually work. And this is one of the reasons why we were like, okay, we have to write a publication paper on it, tell people about this solution. And I want to tell why there's a benefits and why the impact did what it did. So first of all, it's very cost effective. It took us $60 to make the entire thing. $50 went to the entire app and software development side. $45 just for the device. That's all it takes. It does not require internet. Also, you can use it with internet, but it does not require it. You can use it in any remote location wherever you want. It increases the safety of people and, of course, remote location, because it only uses 2G network. It uses a satellite to just track your location and everything. Conclusion. Should I use it or should I not? So yeah, in terms of Bangladesh, definitely. It's something worth using. And in terms of some other countries, I would say in like when you're going to different remote locations and you can't use internet there, this is a very smart solution for a very serious problem. And yeah, so future work I would look for to do is I'll probably make the battery more efficient, and that would making entire parts smaller so that this device becomes something very big. For example, I can give you an example of it. I was static when I heard Apple making that SOS thing. Trust me, I was working on this and I saw Apple do that entire thing, and I was like, okay, I'm onto something, and I want to be somewhere where this is big. And yeah, so yeah. These are my references, and that's it from me. Thank you so much for hearing out my presentation.
Thank you very much. Any questions from the audience? I do. Well, somehow you remove the dependency of internet connection, but then you are relying in two things. First of all, the mobile network, yes, and also the communication with the satellites that provide GPS signal, yeah. So in that case, is at the end you still have some dependency on that system, on that network. So how robust is also against the problems on those networks?
Yeah, you're right on there. The thing is, we are using 2G networks for it. So even though we have that option for internet, but when there is like very little network, it still works because it just requires a satellite network, a couple of bars to just send a message and receive the location. And that location is still read by the app, by the way. Even if there is no internet, if there's a message comes, the app will automatically just update the entire location.
Yeah, because I was wondering, maybe it's not as precise as GPS, but also to rely on the antenna location, like this triangulation from signals, to make it a bit more robust against network problems. Maybe. The other thing is, if I understood well, is like at the end, this is in an Arduino-based system, so it's like an extra device that you have to connect to your mobile phone. Why not to think into an application that internally at the mobile phone it takes the data, the messages that you are using with the location, with the coordinates of the rescue vehicle, and really internally in the mobile phone to compute this position and to show it on the maps. Why to rely on the Arduino? Why not to do everything on board on the mobile phone?
So we wanted to make a device separately that not rely on the phone entirely because that microcontroller was sending everything apart from that, and we didn't just want to make a like a hardware. We didn't want to rely on the phone entirely.
Because
that
if at
also
the end
has
you are relying on the mobile network, is that you are still using a mobile after all.
Yes.
So
Yeah.
that's what I was wondering. Yeah, but very nice, very interesting. And I can see that Bangladesh really is gives an idea why to use those kind of systems with a lot of bicycles there. Yeah. Is there any other question or remark from the audience? No? Okay, we thank you very much. And a nice day, starting day, very early morning, early birthday. Thank you.
Yeah. Thank you so much. It's been great to present between you guys. Yeah. I hope you all have a great day. Bye bye.
Yeah, thank you, you too. Okay, so we have 7 minutes before the last presentation. Time for coffee. Esa no la conocía. La escuela,
No.
es Martín. Ya, Reynoso. Perfecto. Pues un minuto, ahorita iniciamos. Profesor Luis Trujillo, egresado de aquí, de doctor Gerardo. Lucho.
Por eso.
Perfect. Well, welcome everybody for the last presentation in this session of automatic control. This presentation is entitled Passivity-Based Control for Velocity Regulation of a Brushless DC Motor. The speaker is Martin Reynoso, so please.
Thank you.
Can start.
Okay. Let's begin. My title of university is Passivity-Based Control of Velocity Regulation of Brushless DC Motor. Your speaker, Martin Reynoso, my advisors, Dr. Gigamesh Vizraya, the co-advisors, Dr. Luis Garcia Franco and Fabiola Bustos. I'm from to University of Polytechnic University of Pachuca on the UP in collaboration with the ABN. Okay. Well, bien, good. Our presentation is structured by this an introduction and mathematical preliminaries of this work. Next, our parameters, problem statement, and controllability analysis. Also, passivity analysis and classic PVC controller and comparison with the APVC controller. Next, the numerical results and the conclusions and visualizations and bibliography used to this presentation. Now, introduction. This work is focused to the powertrain in the electrical vehicles. In this case, the VLC motor, because of the power density and the low torque ripple, the passivity-based control is proposed due to the powerful alternative to use in this to balance the energy and the analysis systematic stability proofs. Now, two points very important to the classic of the PVC control, passivity race control, and APVC adaptive passivity race control. The first is trajectory talking to the profile velocity, and the next is to reality the low torque compensation. Okay, the next one. We have to start the preliminary mathematics by definition. We have the passivity and the system dynamics. And we said the passivity is the system passivity if this is satisfies the next inequality. This is bounded by the product to the input and outputs. This is this predicts the energy to generate to this, no? Okay. Now the next is the algebra bracket. Because of this is to analyze the controllability of the system. Okay, in this case, provide the key properties for the analysis and control. Next, we have to use tool Clark part transformation to easy the compression of the dynamic system, because of the dynamic of the motor. VLC motor is so very complex because of they have a profile of the EMF profile, electrical motive field. And the problem is the statement because we have this profile EMF. And this the dynamics and electrical dynamics and mechanical dynamics, and rotor motion. This is the parameters considered for the dynamics. Next, the proper statement. We have the transform the in DQ axis part transformation let us the transform the in two variable expressed in two coordinate frame DQ, and then the dynamics is so very easy to use and be in the of the electrical dynamics. Okay, the vector state is considered like this current in the Q, velocity, and the angular position. Next, using the power transformation, we have the system in the affinity control model, where the F, G are the vector fields, and disturbances in this mathematical model. Now, and then the considering the controllability analysis, and we have the construct a matrix, accessibility matrix, by the vector fields Fg and the Lie brackets, and in the first and the second order. And then we verify the property of the we have the rectangular matrix 4 Q 5. Then this property is verified by the determinant the matrix accessibility by transpose, and use the rank of this matrix is for corresponding with the four states to this model. Let's the resulting to this analysis. We had proposed the extra function and the analysis, the feasibility analysis. We have the a positive term. This this indicates this dynamics is not strictly feasibility because of this term. This term is the physically in a relationship with the conversion in electrical to mechanical motion. And the next is the classical design, where the classical design concerning the space state, then the conditions. We have the x1 to 0 and the torque need to necessary to maintain velocity, and the desired control speed or desired control velocity, and this the x4 as the angular position. This is the arbitrary because of the not have the influence of the extra function, because it appears in the extra function. Okay, then we have the proposed extra function in the terms to the x1 to x3. Now we have the two controller to the D and the Q reference frame, and we substitute into the derivative of the extra function. We have the asymptotic complete the asymptotic global asymptotic stability. Okay, can BLC with the dynamic compensation is the APBC. Okay, same the PVC exchange is to fucking following the profile of velocity, and the rejecting the torque variations and the torque variations. Okay, the same, the formalism is like with the PVC. We have the control, the next form. In this next form, we have that compensates the the disturbances, and this let us the tracking the the profile of velocity. Okay, and we have proposed the toroid in this form with the gamma as a positive gain, and the substituting to the derivative of the Stirrer function is similar to PVC. We have the global asymptotic stability, and they reject the Lloyd variations. Now, as a computer results and numerical results, we have a motor with these characteristics, and these parameters. In the first task is to verify the step response, and the first is the PVC chain, and the second is the APVC chain. Let us note the ISO very fast. The APVC ISO very fast comparing with the PVC chain. Now, the second task is the following the tracking trajectory tracking to the profile. This profile is provided by this time, and emulates to the control of the vehicle. Okay, we have to accelerate to we have the normal conduction. And the max speed and the time between time to the 22 and 24 seconds, we apply the disturbances, and the classic PVC shame is not reject this disturbance, and APVC is totally reject these disturbances, and they following the task to provide velocity. Now, the conclusions and directions of the synthetic of this precipitation, we have two control chains, PVC and the APVC. We have a regulation velocity, two asymptotic convergences, and two achieves the velocity and rejects the variation of the disturbances of the torque. As the future iterations, we have to implement this component because, for example, sensorless on experimental variations with the parameters of the real world. Next is the bibliography used to this presentation and the paper. That's all for this. Right. Thank you.
Thank you very much. We have plenty of time for questions. Is there any question? The audience? I do have few precisions. Can you put the question 1 on your presentation? Yeah, when you define that the question 1.
Question 1.
Yes. Yeah, when you define dissipation. I mean, you put that b dot x is less than equal ytu. I think you are missing like less than 0, like to make it passive. It's just a matter of percentage. Now I wonder in equation 16. Yeah, use a precision. Then you define this sort of storage function. Maybe it's not quite related, but somehow to the Lyapunov function. Yeah. This is not a full state storage function because you don't have well, you have x1, x2, x3, but x4 is like missing there.
Yeah, because of this, the state is x4 is okay. Is the angular position, and this storage function is just to the energy of the system. Then the position is in contribution and the energy.
Actually, as a matter of fact, you control velocity, then you have the steady state position.
By the derivation, we have the kinetic energy.
Yeah. Now I just wonder, like maybe at the simulation that you show, are you simulating in at the DQ?
Yes.
Or you are already getting back to the original system, like for a real application?
We have some simulations inverse with the inverse transformation, inverse transformation. In the paper, no including with the these graphs because of not because this graphs is performance to the drift phases, so similar to tracking the velocity profile proposed. So, and this is, in this case, this is started to the DQ reference frame.
Yeah, because it's very common, like you made the simulations at the DQ, but then when you get back, like the part transformation to be suitable, you had a constraint or requirement on the third phase to be zero. And when you had disturbances, that is not always the case, and then you have to talk about robustness, the control system. Because I was just wondering to be sure, like you were going back to the original coordinates. Any question for the audience? No. Okay, well, we thank you very much for your attention. So it has been the experience.
Thank you.
Well, thank you, everybody. With this presentation, we finish this session in automatic control. Thank you very much for your assistance, and hope to see you tomorrow for some other interesting topics. We had the first plenary talk tomorrow at 9, I think. It's an interesting talk about AI applications on image managing for medical purposes. Sounds very interesting. Okay, see you soon. Thank you very much. Yes.